Today I'm going to talk about just kind of sharing actually, because we all experience this, and if we could discuss some of the challenges, and if we may able to as a forum try to figure out how to deal with this situation. So when in October, Karen contacted me um, to give a lecture at NTU, I was very optimistic that I will be able to go to the field soon and will present something new and exciting. Um, but after some delay on the schedule, but then now it's in February, I still didn't manage to go to the field because the pandemic is still here. And so a few weeks ago, I tried to figure out what else to share and still exciting enough for everyone um, here. So I think because it's the 2020 pandemic, I like this figure so much because it's just like the world is temporarily closed and everyone is just like going on their paths and do things differently. And then now we're in 2021, and I don't, we're still not sure yet what to expect within the next few months or years. And so we need to come up with something more um, things to adapt or not um, in terms of how we do things. And so the this figure, the cloud word, is I'm trying to put words into to give you some perspective of things that I do and that might describe who I am. So in the biggest scheme, let me just find my pointer. The biggest word is, in general, I'm a geologist, but then I study earthquake faults, do science, teach, and also some polyseismologists here. But yeah, the biggest part is a geologist. And as a geologist, the field uh, trip, field work is become a big part of how we do stuff. And so these 2020 years have granting us an opportunity to reassess how we as a geologist doing research and what if there's more situation like this happen in the future, then how we survive and how we contribute to the larger social context of what we do stuff and how we can use it to contribute more efficiently. And as an earthquake geologist, of course, the earth doesn't stop moving. And so the earthquake will happen no matter what. It will not follow protocols. And so what we can do in the meantime to anticipate it. And for me as a teacher, I teach at the UGM in the Department of Geological Engineering. It become a point to where we have to decide and how we save our like teaching methods on um, how we train our student and how to make sure that they acquainted to the foundation of field techniques even in this situation. And so that's just to give intro of how this talk gonna be. And so I'm doing most of my work related to active fault and active tectonics in Indonesia. So I moved from, I was trained doing the active faulting research in California, in Arizona, and their climate and tectonic setting is slightly or completely different with uh, where I'm working on right now, but I still gain, I think it's valuable experience to be able to connect to many researcher such as Aaron Meltzner, who's in this forum, with which I wouldn't able to connect otherwise if I didn't get my education abroad and exposed to this community. And so the this figure, just to give you a brief overview of how the the tectonic setting in Indonesia. So we have, so of course you're here, so you experience the same magnitudes of, not magnitude, the same, you're familiar with the area. And so we have this large subduction zone here, and then some collision there, and then other subduction zone over there, and it creates lots of subduction zone earthquake and tsunamis, and also some of the stress transfers to the inland faults here. There's a back thrust there, and so looking at this, we know that this area where my country is very active tectonically, and so that's kind of like the justification of why I am interested to study active fault in Indonesia. And so if you see the how often earthquake happen in Indonesia, we plot only this amount of event, only around 100-ish years. We can see that all of this, um, the islands is covered by these earthquakes. Like can see it. So this color scheme, or the red color is shallow to the bluish color is to the deep part. And even with this, looking at this record only, we can see that the earthquake is really, really um, frequently happen in Indonesia. And the total population in Indonesia is 268 million, so it's a lot. But then the interesting part is that the 53% of it, which is 141 million, is only live in this small island of Java. And so in terms of seismic risks and hazard, uh, the the earthquake affecting more to people in Java instead of other people in other islands in general. But then it didn't. I did not try to put down to the just to give you a brief. Uh, Sometimes I lost in words because my mind is talking in Indonesian. Anyway, Singapore here did not experience direct damage because of the earthquake, but then you also experienced like more into the broader scheme of non-direct effect of the subduction system here. And so if we see here, just this simplified model of the subduction, you would see the distribution of the earthquake that happened on this margin here. Typically you have like the biggest megathrust sequence here, and then on the shallower accretionary prism, you would also experience some thrust faulting there, and then also on the deeper part of the subducting slab, you would also experience intrapat earthquake. But then there's also interesting part where all of the stress is being accommodated by this shallower faults in the inland that might giving more effect to the people, because people live in this area mostly. And so that's that. And then this one over here, just to give you some uh, uh, thing to consider, but this one is only 11 years of record of shallow earthquake, not all earthquake actually, from shallow to deep one, in Java only. And so I put up this figure just to give you a sense of um, those clusters of earthquakes that we can see here, shallow and inland. Those are that presumably associate with uh, faulting on the inland faults. And so if you see from the 150 something inhabitants reside all over Java, mostly on this area over here. This is where Jakarta is. And then Surabaya here. I live here in Yogyakarta. And so we have this nice depiction of seismic activity along this fault over here fault system. And so looking at this cluster of seismicity, then we would expect that uh, the fault is definitely there because the shallow activity of the seismicity is there, means they're active. But then if we go to the field, it's not easy. It's not really easy to find um, this fault. And so I will give you some overview of the challenges that we face as an active tectonics person studying active faults in Indonesia. And so just to give you another background, I'm not sure whether everyone here is familiar with how the seismic hazard analysis work typically. So in here, they can be uh, separated or differentiated into two type of the analysis, the deterministic and the probabilistic, wherein the deterministic will have a site and then you estimate the maximum effect of the earthquake happen affecting your site. While in the probabilistic, then you put some time reference to it so that you will have some probabilistic estimate the um, of the effect exceeding some amount within your area and how many percent within a time frame you can get there. And so in terms of this seismic hazard analysis in us as a geology, we contribute into the these numbers that they put in the probability estimation, including we study and provide information on the fault geometry, the elapsed time and recurrence interval, and also the slip rate. And then that goes into the fault segmentation information about how big is the fault length, and then that will use for the estimation of the maximum magnitude of the earthquake on that fault. And so this information then collaborate into the long-term earthquake potential, and then also goes into this number over here. And so this is the geology part contribution. And so in a simple way of how geology methods used for active fault mapping. Usually we are conducting surface mapping using high resolution topography data, including LiDAR, UAV generated aerial photo, and so also field mapping, and then subsurface mapping using geological methods, geophysical methods, and um, uh, seismic data, and then also the analysis of the seismicity contribute to the understanding of the whole system. And when you see this uh, range of methods that are commonly used, then you see that the field, the requirement to visit the field and map it is becoming a large portion of what we do as a geologist. And so this COVID-19 pandemic was that limiting our accessibility to go to the field and do this type of methods is really affecting us in general sim. And so here I will, before we get into the challenge of the COVID-19 pandemic situation, I would like to just give you a tour about what are the challenges aside from the COVID-19 on studying active faults in Indonesia. And so here in Indonesia, of course, you also have it in Singapore. We have a high rainfall per year. So we almost 2 meter per year rainfall. And that creates a high erosive environment to start with. And so putting that together with the slow slip rate of the faults, that creates the erosion outpace the displacement. And so sometimes we can't see the result of the deformation easily. And so in another, not problem, another thing is that the quaternary volcano is abundant, especially in Java and Sumatra, so that you would have also the volcanic deposit that coming out from those volcanoes, those also creating rapid aggradation, which also obliterate most of the vertical displacement that we might want to see. And also, of course, with the large number of population, we also have high developed region. Over here, you can see that this one is in Jakarta. You can see that even the morphological features such as river here, you can't really see it again, covered by all of these housing and buildings. And also, I think it's happened anywhere in the developing world, but we also have like limiting grant that allow us to do high enough resolution of the data that we want, because of we have such a limited lab access, and especially for dating analysis, not many we able to date within the country. So we have to go and send it out of the country to get the data analysis. And so this map over here is to put you into perspective of how the volcano affecting sedimentation on the island. This is Java, and this red, the solid red colors are the volcanic and volcanic center and its associated um, lithology. You can see that most of it are covered into the extent of this rocks. And so sometime our somehow, if not, if the fault near um, did not displace this unit, then we have to search on the yellowish color um, extent of deposit then, but those are also limited because of the aggradation of this material that coming from the volcanoes. And so this one over here, I like to put this every time I give a talk because it's funny. This one is in Semarang in Central Java, and this is Raymond Aerosmith, my former PhD advisor. We um, we did our mapping from the older aerial photo, and from it we able to identify that there's a fault there, and it was really clearly visible on the older photo set. But then when we go to the field, then it's already everything is already covered in buildings. So the fault is like along this region. So we have to like go into someone else properties to just kind of searching for outcrops. And this one over here is to give you a picture of how the volcano affect the sedimentation pattern. This one over here is the Merapi mountain. Those behind it is the less active Merbabu volcano. This is close to Yogyakarta city where I live. This is the university where I'm working on, Gadjah Mada University, and so you can see that it's in the foot slope of this volcano. And so this volcano is considered one of the most active volcano in the world, and every now and then this volcano just erupting and putting sediment on this basin over here. And so this evidence of older civilization that get buried by laharic deposit of this volcano give evidence that the sedimentation rate is pretty high within this basin. So this one over here is this university called the Islamic University of Indonesia. They want to build this is their new library, and so they have their plan layout and they want to build it in this place. But then when they try to dig for the foundation, they found this temples, and so because of the rules, then you can't build anything above the archaeological site. So they have to modify their design, and so they now really interesting because the library now have a temple on the courtyard, which is cool. So if you go there, and you will be able to visit this site. And this below one over here, this is the Kadulan temple, which is the date age around 780, and so it is covered buried under at least 6 meter of Teklaharic deposit. And what interesting about this site is that before they start rebuilding um, this temple, the lower part of the foundation it's undulating, and so um, it was to me when we see it, we thought that those might be represent the damage caused by the seismic movement, because otherwise it will be just like collapsing. If it's because of the lahar, then it should be all over the place. But then those stack foundation that represent appears like a seismic wave coming through those and creating those damage, and then subsequent laharic deposit covering it is the cause of why this temple was abandoned at the time. And but yeah, that's now this temple is already reconstruct, and now it's very nice, and you can visit there when you visit Yogyakarta. So that's that. And then another challenge is that the soil production is really rapid in Indonesia. This is a geologist for scale here. You can see that all the way to the top of the hill, all the way down there. It's all soil, weathered bedrock, creating this thick soil. So you could imagine that if you have something um, related to active deformation with only few meters of uh, uh, movement, then it will be fastly eroded and can't really see it. And then also we have the vegetation cover, of course. Like you, this is example of how we conduct our field work. Covered, we have to find the fault there. We know that the fault is there based on the topographic break, but then when we go to the field, then that's what we face. Like lighter would be nice because we can remove the vegetation. And then also we have high rainfall, and so flooded trench, polyseismology trench is what to expect. And also we sometimes it's not easy to find datable material because of the lack of quartz bearing rocks for ASL, because we have such of this it's more andesitic volcanic product here. We don't really um, found many batholite or um, like more granitic rock anywhere, especially in Java and Sumatra frontal part. So we didn't get much of quartz bearing rocks for OSL. And also the tephra is quite weathered, so it's not really work for the radio metric dating. And so we mostly rely on the C14 analysis usually. But then whenever we open a trench, then we usually came up with this problem of the uh, groundwater entering the trench. And so this one over here, I was in the hole, and so sometimes people have to keep an eye, otherwise it will be like the water level will filling the hole quickly within hours or so. And so that's the challenge. And another challenge is also even with the deep uh, groundwater, but then when the rain came, then it will also become problem. So this is an example of what we did, and we trenched the Paukoro fault along the rupture from 2018 earthquake. So that was nice because we know where the fault is. Usually we can't really pinpoint normally, but then because of this earthquake, then we know exactly where the fault. So we it's making us easier to look at our polyseismic trench. And so we opened the trench. This is a massive one, around 5 meter deep trench, and we lucky enough that the groundwater table didn't come up at this site, because that's why we chose the site, because based on the geoelectrical survey, it shows that the groundwater table is at 15 meters below the surface. So that's good for our trench. And so we open this trench, we expose this beautiful rupture from the 2018 earthquake here, displacing this alluvial plain, alluvial deposit. You can see the lateral displacement of the fault. And so we finished logging this nice trench. We locate some samples for the radiocarbon, and then we had lunch. And then the rain came, and after 15 minutes, this is what we see. And so our samples are gone, and that was quite disappointing. So what we did was we have to redo the mapping and sample collection, but we lost most of the lower bench data there. But at least we get to the note here is that if you open a trench in Indonesia, then you have to work fast for quickly, because before the nature takes over. So that's that. And then another challenge is that the human modification for the landscape. There are lots of miners, rock miners in Indonesia, and especially for taking only the rocks and not the the deposit, like gemstone kind of things, but they just take the rocks for buildings. And so those operation, usually they tend to follow weakness along a fault zone because it's easier for them to cut through. So this area is also, like, for us as a geologist, we try to race with the miners, because we want to get the structural data, but then within days they will be gone by the operation. So we have to move fast in documenting the site. And so this one over here, it's an active strike slip fault in the northern part of central Java. You can clearly see that there's a horizontal striation there. And that's my former advisor there. And yeah, we have to do it fast if we want, because the next few days after we took this picture, we went there and it's already gone, the outcrop. And so using piece of all of these challenges, so we figure out that the common way of doing active fault mapping is not all applicable to Indonesia because of those challenges condition. And so we try to figure out what are the other methods that might work for the area. And so I tried several methods, and here I would like to just kind of lay out and just kind of give you some picture whether this might work or not. And so the first thing that I'd like to present you is the morphometric analysis of the bedrock channels. So in here, it based on the empirical data that using the scaling of this relationship around the globe. it's following this. It's called the Flint's law, where the slope, well, there's a linear relationship between the slope and the area and also the concavity value. So you would see here in a steady profile of the channel, when you have a steady profile, then the slope of the log area and the log of the slope is, it shows linear trend without disturbance there, even though the channel concavity, even though the steepness of the profile is different, but they have similar trend um, on the slope of the plot. And so based on this, then you would have the people come up with the solution that the concavity is invariant with uplift, while the steepness, the slope is varies with uplift. And so if you have disturbance of this KS value, then you would expect that something affecting the profile value, more or less like that. So if you go to this, there are plenty of reference on this. And so using these methods, oh yeah, this is just to give you point of what I'm trying to explain earlier. So you have drainage area, gradient, put it in log plot, and then if you have something that is unlinear, there's a break there, then you should expect something disturbing there, which is my associated with faulting. So it's coming from the same area. And then if you plot it into the average KS value, then you would see something high KSN and then low, sudden, abrupt change in the KSN value there. And so that's where you put your plausible location of the fault. And so using that background knowledge, then we use it for studying the Chimandiri fault in West Java, where there's the fault is active based on the seismicity, but the surface expression of the fault is difficult to pinpoint. Like if you go to the field, then it's not easy to find the fault. And so I'm using this method just to help me to locate where the active strand of the fault is. And so this is the result. And so you can see here the reddish color mark the high KSN value. So anything higher than 100 is usually considered as a global agreement that those are high. And so it could also affected by the lithology. So we also do the comparison with the lithological, the geology map to see if the abrupt change is also coincidence with the lithological condition. And so we took out those that are coincident with the abrupt lithological contact and use the other that does not. And so based on those observations, then we were able to identify that there are several areas of high KSN value separated into several boundaries, but then we still cannot really pinpoint where the fault is. And so we use nick point analysis together with those analysis and came up with the location of where the fault might be. And so we also combine with the field observation as well. And so using that methodology, then we able to put the fault lines on the map, but then we need to figure out at some places we able to find the fault phase in the field so that we can confirm the kinematic, but then on the other part of not on all of the faults. And so what we do next is we do the modeling, the elastic dislocation model to see if what if we put it as a strike slip, what if we put the fault as a dip slip, and do some modification on all of this fault and see which one is agree with the topographic assemblage characterization of the fault. And so we came up with this model of the fault that it's involved the side strike slip. It also involve reverse faulting mechanism. And so based on the study, we're able to segment it, the Chimandiri fault into these 6 fault segments, which previously only considered as a single segment. And then using the empirical model, then we came up with this estimate of how big the earthquake might happen on those faults. And so it's a published study, so you can see it there if you're interested. And also, we also try to do polyseismology study in Indonesia. I conduct several studies. Not all of them are successful because of those challenges. This one over here is quite promising, and the result is also in compared to other places in Indonesia, it's quite I would say successful. Of course, if you compare it to San Andreas sequence or more into arid environment result, then this might be some challenge to but this is the best we can get. And so in the northern part of East Java, there's a fault that displays this deltaic deposit here. The fault is clearly visible at the surface, and so we dug a trench there, 2 perpendicular trench. I think it was like 200-meter long trench, and then we identified several faulting. We took samples of the charcoal, the tridal charcoal for 23 sample, and configured this earthquake model for the site. And so we able to resolve 5 earthquakes within 400 years of worth of sediment there. And you can see that some of the data is have a wide uncertainty, as such as this even 5 here is not really helping much because it have a very wide uncertainty there. And so using those data, this one over here is pretty good. We have a rough recurrence interval of every 300 years, and also the maximum 6.6 minimum estimate based on the survey, the inland fault strand rupture. And so another study that we do is along the Aceh fault in the Sumatran, the Great Sumatran Fault System. It's over here. Previous study said that this fault is a single along its 250-kilometer long fault is considered as a single segment. So that didn't quite match with the historical record, because a 250-kilometer long fault will equivalent to around 8 to 8.2 magnitude earthquake, which is not really the case for the Aceh fault. And so we studied in detail and see if there's any indication of segmentation there. And so this one over here, just to give you that in few months ago, there's a earthquake swarm here happen along this fault, and those are the high strain area there. And the evidence of right lateral strike slip faulting there, we can see it here, that you can see this river over here, and there's a nice subtle ridge there. When we try to retrofit back to put it back into its original estimate of original position, then there's a 48 displacement there. We can see. This one is using the aerial, the UAV model of the site. And also based on those study, we able to update the segmentation model for the Aceh fault, and now it's we can revise it into 8 segment, 7 new segment based on this model, and then we update the estimate maximum magnitude for the fault. It's also a newly published documentation there. Okay, so back to the COVID. After I take you to Java, Sumatra, and Sulawesi, and now the effect of the COVID-19 to what our ongoing research. Of course, the first thing is that it causing the delay and cancellation of fieldwork plan to collect data, and then also some loss disruption of the long-term data set, topographic marker, and also everything else related to the real-time monitoring effort. And also it limits international collaboration because of the travel restriction. And so during this past year, I supposed to go to the field and collect data for several projects, but we have to cancel, and some of them are the study about the source to sink environmental signal propagate from the Barisan Mountains into the Forak Basin in Western Sumatra. We did our preliminary data collection. We supposed to arrange a deep coring this past year, but after everything ready to go, we got the drilling company ready and permission ready, permitting everything ready, but then the COVID came, and so we have to halt the projects for that. And also in collaboration with the NTU, AOS NTU, with Dr. Aaron Melsner here, we're supposed to start doing our collaborative research um, uh, on the quantification of the hazard from the rising sea and earthquakes in this area over here, including in Indonesia. And I was involved with Aaron to work together on this part of the study, but then we didn't get the chance to do that yet. And so hopefully next year or so we can get back to it. So that's that. And then looking at those challenge and struggle, what we can do. And for me, we need to ask ourselves, can we pursue the research objective with the existing data? If not, what are the alternatives? Um, my takeout here is that you should map the free to open databases, contacting other researchers for any available data. And also, if needed, then you have to get your feet on, learn the new methodological or analytical techniques. And so what we did in the meantime, where we cannot go to the field, then you can do analysis of remote data, such as this one over here, the Mamuju earthquake recently. Um, we can do analysis on the aftershock sequence, and this work is submitted and is in review right now. So at least without even go to the field, we can use existing data and new data set and create something useful from it. And also, I like to point out that there are several sites that you can get data for free, such as DEMNAS. It's the high enough resolution digital elevation model for the entire Indonesia that you can get for free. And so it's an 8-meter resolution data set that you can tweak on playing on other mapping. Um, like for example, like the morphometric analysis of those active fault zones that you can try to play even if you didn't get the chance to go to the field. And also I like this data from like the website from Open Topography. USGS also have some seismicity data, and also our scope for other data as well. And so you need to be creative and see if you can work with freely available data and create something meaningful in terms of research. So that's that. And then also moving forward, I think we need to utilize technology that we need to create high resolution photographic database, even with the cheap methods such as the UAV or even fancier using LiDAR scanner and create a 3D geological and sedimentary archive, including like sampling, keep the sample until you can do something about it in the future. And also those effort of creating a standardized archive of data and interpretation so that um, we can promote open data framework and collaboration so that the community effort of interpreting data in a site can be established uh, there. And also, I like this figure over here. This is from Scary et al. Publishing in 2020 about this subject as well. And so, because the earlier slide that I it's only a short-term solution. So what are the long-term solution for this? And so several take out lesson that we can get from this pandemic is that in a collaboration that involve multi countries and international um, institution, then it is important to appointing leadership to in-country research collaborator at each field site location so that when something happened that restrict travel from other part of the part of the collaborators, then your work is still somehow able to survive and the data collection still able to be conducted either way. And so another take out I think you need to promote open data framework and community-driven interpretation and collaboration. Though, although the platform is, I don't, we need to figure out what the best platform to do this and how the arrangement of um, the what you call it, like the intellectual properties of those interpretation need to be assigned. And also in terms of teaching, we need to expose our student to, I think it's important for them to expose to digital archives and also their interpretation. And so we can simulate the field training for the student and that will help us transferring knowledge and training and also developing new methods. We need to do that as well. And so those are the future plan. So in summary, I feel like the short-term and long-term adjustment is necessary to keep the productivity of the research and the effectiveness of the student training and mentoring in anticipation of prolonged pandemic, because we didn't know how long this one will go and um, resume our activity. And also back to the fault study in Indonesia, identifying active faults in humid environment is challenging, but it can be done with some limitation. And one of the biggest challenges find suitable dating techniques. I feel like here we can see the amount, but we in terms of the timing we somehow limited. And also, the exiting challenge of identifying active faults in humid environments still prevail, but collective critical thinking to develop new methods of observation and data analysis is needed. And it needs to support it from the modeling aspect as well to understand the process. And because sometimes surface expression of faulting is obliterated, and so application of multiple surveying methods to obtain surface and subsurface data to support interpretation is crucial. And also, it's important to establish an agreement within the research community to create a standardized archive of data and interpretation and promote open data framework and community-driven interpretation and collaboration. And so that's what I'm sharing today. Thank you for your time.